before I have the chance to have any roots. So it's also possible that I could have 0. Cool? Are we cool?
Yep.
All right, last two. Now, I start at -2. And then the negative 5x term brings me down. And then eventually, no matter what, the 3x squared term will take over. So guaranteed 1 positive real root. And now here, this is the just rags to rags to rags story, right? This is like, started on the bottom, got worse. Always, whole life, down, 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 down. All right, 0. All right, so we have now fully cataloged in a beautiful picture a family tree of polynomials with all different front group table. Can you like heads like down to the table or something like that? Yeah, good. And so we have fully cataloged all possibilities. So what I normally do is stop for like 5 minutes now and let you guys all conjecture, but we have no time for that. So we just have to know the answer now. Who knows? Shrish?
Whenever the sign changes.
Yeah! Shrish, you figured this out by just common sense, or you like saw it in the book or something?
No, I know it before.
Yeah, Shrish just like knows things. Yeah, what Shrish know? I should have left that back in. Well, who cares? Screw period 8. No, not screw period 8. Take it back.
Cut it out. Take that part out.
Love you, period 8. Yeah, look, what Shrish says is, yo, whenever the sign changes, we might get a root. Because watch, here we start at 2, right? And then it's just like bigger, bigger, all the way up to 0, all the way up. So the sign never changed, the sign as in like the switching between positive and negative. But here, since we're positive, and then we stay positive, as soon as I add in each new higher powered term will dominate eventually the lower powered terms before being then dominated again, right? So when we switch from this being positive to being negative, that's what causes the graph to sort of then turn and start going down in the other direction. Every time the function is positive, but then a new negative term comes along to say, no, now start going negative, now the function goes back down and so crosses. Here again, right, we start positive, then comes negative, then positive again. So as there were 2 sign changes from positive to negative and from negative to positive, that tells me that there are going to be 2 roots, or maybe 0. And over here, positive, then negative. So we went down, right? One change from positive to negative. And it just keeps going, right? Here we're negative, there's a change from negative to positive, so that change says start going up now, and we cross the x-axis. And it keeps happening. All right, this has a name. Can you move the camera over here and like kind of zoom in a little bit? This is called Descartes' law of signs. No, rule of signs. Descartes' rule of signs. And it is a theorem which I have essentially just proven, or kind of like I basically talked it out, proved it to you, that says when you will expect certain positive. When you will expect a certain number of positive real roots. Here's what it says. For polynomial p, with real coefficients. For a polynomial p with real coefficients, in other words, the only kind of polynomials we care about, with the terms listed in descending order of degree. In other words, write the polynomial the normal way you normally write it. Well, the theorem, to apply the theorem, you need to write the polynomial the normal way. Then, here's the theorem. The number of positive real roots is equal to the number of sign changes in the coefficients of p. again, we've seen that that's not actually correct, right? Because over here, 2 sign changes predicts 2 real roots, but that might not happen because it might not have enough power to get over the x-axis. So then we add in a little or less than that by an even number.
It's not very concrete, that's just passive.
Okay. Good. 5 minutes left to do 2 examples.
If it's cubic, it has to be 6 minutes.
Okay. Take, and someone flip the camera after a pause of a minute or 2 to let people write that down. 5x cubed minus 3x squared plus x plus 2. Alright, flip it. Let's talk it out. How many positive real roots does this function have? Well, if we think about what's happening, right? What's happening? We have this function. It starts at 2. What effect does the x have? Makes it go up. What effect does the negative 3x squared have? Makes it go down. And now maybe it goes down enough to cross the x-axis and maybe not. This is like a cloud hovering over my function. But eventually the 5x cubed term will dominate and will bring this thing back up again. Do you agree? So Descartes' offside says what? There are either, maybe there are 2 positive roots, or maybe there are none. Those are the only 2 options. Agree? Okay, now here comes the tricky part. After all of this conversation, I now can predict the number of positive real roots. But I also want to know the number of negative real roots. In other words, I would like to shine a light onto the left-hand side of this function, which is clouded right now in darkness. What do we do? What do we do, Shrish? Because he knows things, because he cheated. Shrish!
We plug in negative.
Yes, Shrish is like, aha! What I shall now do is to define a new function. Perhaps we call it like g. And g is just f of negative x. What is f of negative x you learned in Precalc A?
It's
Flip over the y.
You flip over the y-axis. And so we can just compute f of negative x by just plugging negative x in. What do we get?
negative 5
Negative 5x cubed
minus 3x squared
minus 3x squared
minus x
minus x
plus 2.
plus 2. Well, this function g is its own function. And so this function g, which is really just f of negative x, we can also graph it. And we can apply Descartes' rule of signs to this g function. The g function starts at 2. And then what does the negative x do?
Down.
Makes it go down. What does the negative 3x squared do?
Down.
Down and down even more, right? And therefore, what I can say for sure about the g function is that it has precisely 1 positive real root.
Negative?
No, careful. G. I'm talking about g as if it's like its own thing now, man, right? G, by Descartes' law of signs, rule of signs, has exactly one positive real root. But g, the positive half of g, just is the negative half of f. Because that's what g is. I defined a function g to be f of negative x. Therefore, if I know what the right-hand side of g looks like, I know what the left-hand side of f looks like. What does it look like?
Down.
Down. Therefore, I can say for sure how many negative real roots f has. How many?
1.
1 guaranteed. Good? Okay, and then we make one more column in this chart, which is by the fundamental theorem of algebra, there have to be 3 real roots. 3 complex roots. So if there are 2 positive and 1 negative, then how many non-real are there? 0. And if there's 2. So that completes it. Okay, last example before the bell rings. Here is a function, negative 6x to the 4th plus 3x cubed minus 2x squared plus 5x minus 3. Make the chart. Find the number of positive real roots, find the number of negative real roots, and then you're